Okay guys, let's get started. Good morning. Welcome to COE3001 Mechanics of Deformable Bodies. First, let me introduce myself. My name is Yazuo Lu. I am currently a PhD candidate in the Department of Mechanical Engineering. You might feel it's a little bit strange to have a student instructor standing up here instead of a tenured professor, but honestly, I think having a student instructor has some huge advantages for you. The biggest advantage is that I have been in your shoes not too long ago. In fact, about 7 years ago, I was sitting exactly where you are sitting right now. I was taking this exact class, stressed about the exact same exams, and trying to understand these exact same concepts. Back then, the course was actually called Mechanics of Materials. Today, we call it Mechanics of Deformable Bodies, but don't let the name change confuse you. Materials and deformable bodies are exactly the same thing. Why do we call it deformable? Because in the real world, nothing is truly rigid. In your statics class, COE3001, you assumed things were rigid blocks that never changed shape. But here, we accept the reality. Every material is deformable. Every material deforms when you push on it. And that is what we are going to study. Now, I mentioned being a student instructor has advantages, but to be honest, it also has disadvantages. The main disadvantage is that I'm still learning how to be the best instructor I can be. I actually taught this same class last semester. After the course ended, I spent a lot of time looking at my teaching evaluations. My overall score was 4.6. Most students were satisfied, but I read the comments very carefully and there were some students who aren't happy with my teaching style. The most common complaint was I made this class too hard. I want to address that right now on day 1. Look at the course code, COE3001. It starts with a 3. If a course starts with a 3, that means it's a core course for your entire engineering career. It represents the transition from basic science to real engineering. I know we have a mix of majors here. Raise your hand if you are civil, aerospace, mechanical, biomedical. Right, you all come from different majors within the College of Engineering. But whether you are building bridges, airplanes, robots, or medical implants, the bottom line for all engineers is the same, which is safety. If you learn this course well, if you build a solid foundation, you will be able to design structures that are safe and efficient. You can sleep at night knowing your design won't fail. But if you don't grasp these concepts, if you just try to memorize formulas without understanding the physics, you may design something that leads to a disaster. We aren't just doing math problems here, we are learning how to prevent planes from falling out of the sky and bridges from collapsing. We will actually look at some famous engineering disasters later in this lecture to show you the cost of bad mechanics. So yes, this material is serious, but I listened to the feedback from last semester. I don't want to bring you with unnecessary difficulty. My goal this semester is to reduce the difficulty slightly, but this is important. I'm not going to make it easy by skipping the hard stuff. Instead, I'm going to change the focus. I will focus less on tedious, complex calculations and focus more on the conceptual understanding. I want you to understand why things deform, not just how to punch numbers into a calculator. It's a trade-off. I want to make the course manageable for you without making it useless. I hope that sounds fair. I really hope you can enjoy this course and ultimately use this knowledge to enjoy a successful engineering career. Okay, now let's shift gears and talk about how this course actually runs. We need to go through the general information. By now, you should have already received the syllabus. If you haven't, please check Canvas immediately after class. I want to be clear, everything you need, all the lecture notes, the assignments, and the detailed solutions will be posted on Canvas. However, Here is small catch. While everything is posted, not everything is available right now. For example, homework solutions will only appear at a scheduled time, usually 2 days after the due date. So keep an eye on the schedule. That's the end of your syllabus. Now, regarding the textbook, we are using Mechanics of Materials by Gear and Goodnow. I'm referring to the 9th edition. I know textbooks are expensive and I know versions change. I want to assure you that different editions are totally acceptable. If you have the 8th edition or another version, don't worry about it, because I will provide the full context for every homework problem. You won't need to hard for problem 3.1 in a specific book just to know what the question is. I'll give you the question. Also, the lecture slides follow the logic of the textbook very closely. So if you are the type of student who hates reading long, dense paragraphs in a book, just focus on the lecture slides. It's actually good enough to succeed in this class. Okay, here's the office hour. Currently, I have them scheduled for Mondays and Wednesdays from 12:30 p.m. to 1:30 p.m. The location is MRDC 4114A. Please pay attention to the A. It is the room next to the meeting room. There are two 4114 in the building, so don't get lost. I also offer online office hours via Zoom if you really can't make it in person, and you can schedule those by appointment. But there is my strong recommendation. Please make full use of the in-person office hours. Why? Because communication is about more than just the equations. When we are on Zoom, we lost a lot of information. For example, the body language and the look on your face when you are confused. In person, I can see how you are feeling about the material, and we can solve problems much faster. So come to MRDC 4114A if you can. A quick note on prerequisites. You need statics and differential equations. I know differential equations sounds scary to some of you, but let me set your mind at ease. Although it is a prerequisite, we will not be going deep into complex math theory. In this course, the differential equations we use are elementary. Honestly, 90% of the time you are just solving equations by simple integration. You don't need complex manipulations. We will introduce a little bit today in today's lecture, and you will say it's not difficult. So please don't let the math make you feel uncomfortable. Now I want to talk something that is not written in your syllabus yet. This is a special edition I'm designing for this semester, a mini project. Why I'm doing this? Well, I look at the teaching evaluations from last semester and noticed a pattern. The midterm exam is worth 30% of your grade. Some students didn't do well on the midterm, and then they felt hopeless. They felt that, well, I messed up the midterm. I guess I'm going to fail the class, and they give up. I want to prevent that. I want to give you a chance to recover. So the idea is this. If you don't do well on the midterm, you can choose to complete this mini project to earn bonus points and improve your score. The project is simple and honestly is pretty fun. The challenge is to design a bridge using letter-sized paper only. No wood, no metal, no glue reinforcement. Just a standard paper. But here is the catch. This paper bridge needs to sustain a load of 10 kilograms. Think about what 10 kilogram means. If this textbook is about 1 kilogram, you need to stack 10 of these books on the top of your paper bridge without it collapsing. It sounds hard, right? 10 kilogram is a heavy weight for just the paper, but it is physically possible if you understand the concepts of stiffness and stability that we will teach in this class. I will make a formal announcement about the rules later, but keep this in mind. If you do great on the midterm, you don't even need to worry about it. But if you slip up, this is your safety net. Okay, let's move to the grading policy. We have 10 bonus points available in total. 6 of these points come simply from attendance. Now, attendance is not strictly required but is highly recommended. I will perform 3 random attendance checks throughout the semester. The math is simple. If you appear once, you get 1 bonus point. Appear twice, 3 bonus points. Appear 3 times, you get the full 6 bonus points. I know that you are thinking, it's 8 a.m., it's cold, I want to sleep. Trust me, it's early for me too, but think about the math. Imagine that at the end of the semester, your final score is sitting at 89. You are 1 point away from an A. If you missed these attendance points, that 89 stays a B. This is a painful situation to be in, so I strongly suggest you come to the class. It's the easiest 6 points you will earn all semester. Next is homework. We have 6 assignments, each worth 6 points. I will drop your lowest score so we count the best 5. There is another bonus opportunity here, typed assignments. For each homework, if you type your solution using word equations or the text like overleaf, I will give you 1 extra bonus point. The maximum you can get here is 4 points total. Why do I care about if you type it? Because you are engineers. It's critical for you to communicate efficiently. If you are handwriting your homework and your formula is messy, or your 2 looks like a Z, people can't understand you. In the real world, if you send a report to a rigorous department or a client, it needs to be professional. So I want to encourage you to practice using tools like LaTeX now. Plus, it makes it much easier for the grader to give you points if they can actually read your equations. Well, we have 1 midterm exam and 1 final exam. These are closed book exams, but you are allowed to bring 1 equation sheet. It can be a letter sized and you can write on both sides. However, I have 1 strict rule for this sheet. You are not allowed to copy homework solutions onto it. The equation sheet is for formulas and concepts, not for simple problems. Why? Because the homework solution helps you to understand the problem. It's not a replacement for your brain. If you just copy the solution, you aren't reviewing. I want you to use the time preparing your equation sheet to actually review the materials. Trust me, if you rely on copying solutions, you will struggle in the exam. Finally, and this is very important, the generative AI. Our policy is a bit different. You are allowed to use AI like ChatGPT, Gemini, etc. in this class. But, and this is a big but, it is limited to clarifying concepts or reviewing materials. You cannot use GPT directly to solve your homework. If you submit work that is generated by AI, that constitutes academic misconduct, and it is strictly prohibited. Let me tell you a story from last semester. I know there were some students using AI to do their homework. Their homework scores were perfect. They looked like genius. But then comes the exam. The exam is closed book, no internet, no AI. I put a question on the exam that was almost exactly the same as the homework problem, just with different numbers. And those students, they couldn't solve it. Why? Because they had magic tricks during the homework, but they couldn't bring their magic tricks into the exam room. So please use the homework to learn. Struggle with it a little. That is how you pass the exam. Lastly, the late policy. Unless you have approval, late homework gets a 30% penalty. And remember, I post the full solutions 2 days after the due date. Once the solutions are posted, I obviously cannot accept any more submissions. That would just be copy, right? So that's the logistics. I know it's a lot of rules, but they are here to make sure everyone is treated fairly. Any questions before we move on? Alright, let's dive into the core of what we are actually going to learn this semester. I mentioned earlier that we have 4 main topics. You may just see a list on the screen. but I want you to really visualize what this means in the real world. Topic 1, bars. First up, we have bars. What exactly is a bar? In engineering terms, a bar is a structure that is long and slender. Think of a long cylinder or a long rectangular strip. Because it's shaped like this, it's not designed to take loads from the side. It's designed to sustain load along its longitudinal axis. We call this axial loading. When you pull it, that's tension. When you push it, that's compression. This is simplest form of deformation, but it's a foundation for everything else. Think of the cables on the suspension bridge or the truss members in a roof. Those are bars. They are either being pulled apart or squeezed together. Topic 2, shafts. This is where things get a bit more interesting because we introduce rotation. Think about using a screwdriver in your daily life. When you use a screwdriver to tighten a screw, what are you doing? Are you pushing it? Are you pulling it? No, you are applying a twist. You are applying a rotational movement, which we call torque or moment. Unlike the bar, where the length changes. In a shaft, the length doesn't change. Instead, the material twists. We need to understand how much it twists and whether the material will shear off under the rotation. This is crucial for anything with an engine or a motor. Right. Topic 3, beams. We call this bending. We call this problem as bending. Look up at the styling of this classroom. Right? There is a structure holding us, and the people on the floor above us up. From our perspective, that is a beam, right? Think about the load. There are people walking on the floor above. Their gravity, their weight is pushing straight down, but the beam itself is running horizontally. So the force is perpendicular to the structure. When you apply a load perpendicular to a long structure, it doesn't just squish, it bends, it curves. This is a completely different deformation state. The top of the beam may be getting compression while the bottom is getting tension, or the top is getting tension, the bottom is getting compression. It depends on the direction you bend, right? We call these complex states bending, and you will see this everywhere, from bridges to bookshelves to airplane wings. The topic 4, columns. Finally, we will come back to the compression, but with a twist, laterally, actually. We call these columns or stability. Image that a tall, thin concrete column. If I push down on it really hard, what will happen? Does it just get shorter? If it's thin enough, actually no, it will suddenly bow out. It will curve to the side. We will call this buckling or loss of stability. Even if the material is strong enough to handle the weight, if the geometry is too slender, it's too thin, it becomes unstable. Think about it. If you saw a building column that was curved like a banana, would you feel safe? No, right? It looks dangerous. It looks bad. So stability is a critical design factor. We won't just calculate if it breaks, we calculate if it holds its shape. Now look at the flow chart on the screen. I know it looks complicated. It's a lot of boxes and arrows. Don't panic. It's totally okay if you don't understand this roadmap right now. It's the first lecture. You haven't learned the material yet. But I want you to have this big picture in your mind. We are going to build this map together throughout the semester. Here is the logic we will follow. First, we start with the load, which is actually the external force. Then we look at the deformation, because the deformation is the answer from physics. It's how the real world reacts. We determine the internal forces and we relate the stress and strain using the material properties. Later, we will study Hooke's law or the constitutive relations. Finally, we check out the three conditions. Is it strong enough? Is it stiff enough? Is it stable? We will revisit this picture again and again and again. By May, this messy chart will make perfect sense to you. So, why do we bother calculating all this math? Why do we learn about stress and strain? Look at the video playing on the screen. This is a numerical simulation of a 2012 Toyota Camry crash test. This wasn't filmed with a camera, it was calculated by a computer. The computer solves the physics, the laws, the material properties, just like we will learn to do in this class, but much more complex, right? I want to ask you a question. If you were to do this experiment in your real life, you take a real Toyota Camry and crash it onto a wall, how much you think that one experiment would cost? Well, someone say that maybe the price of the car. Sure, you destroy the car, but what else? You need the wall, you need the facility, but actually the most expensive part isn't the car, it is the sensor, and specifically the crash test dummy inside the car. To study a crash, you need a human model inside. This dummy is packed with incredible sensors to measure accelerations and force to see if a human would survive. If the acceleration is too high, the human gets hurt. These dummies are extremely expensive. It's much more expensive than the car itself. And think about the aftermath. You crash the car is destroyed, the sensor may be damaged, the data acquisition system is expensive. An industry estimate for a single hypothesized crash test is around 50,000. Like 50,000, you only get one data set because you only do one experiment. Now look back at the simulation on the screen. How much does this cost? Right? Of course, you need to pay for the electricity, you need to pay for the computer license, and you need to pay for the engineering salary, right? An estimate maybe 5,000, right? That is only 10% of the cost of a real experiment if you do the numerical simulation. This is why this course is important. If you understand the physics, you don't need to crash 100 cars. You can run 10 simulations. You can use simulation to improve your design. You can say, oh, this part is too weak. Let's check it. Let's strengthen it in the real model. Or this part is too stiff. Let's change the material. Your perfect design, your perfect design is on the computer. Then when you are confident, you run one real physical experiment to verify it. If the experiment matches your simulation, you are good to go. You start production. You just save your company $500,000. Now, obviously, modeling a full car crash is too difficult for COE3001. That's graduate level stuff. But we will do a small version of this. Later in this semester, I will introduce a small project using COMSOL multiphysics software. It's available on the Georgia Tech VLab, so you can access it from anywhere. We will look at a simple wedge problem. I will ask you where is the most dangerous part of this wedge if you apply a load. You run the simulation and you see the red color, that indicates the high stress. Then you will use the hand calculations, the analytical equations we learn in this class to verify the results. You will see that the math matches the pretty colors on the screen. That is the moment you realize that the math actually works. So that's our goal. We learn the theory so we can understand the tools that build the modern world. Okay, so we have talked about the abstract concepts, the strength, the stiffness, the stability, but honestly, Those are just words on the slide until we see them in action. I like to say that mechanics of materials is the hidden backbone of civilization. Why? Because every time you see a super project, a skyscraper, or a rocket, the only reason it is standing there and not collapsing uh, not collapsing is because an engineer somewhere calculated the stress and the strain correctly. Let's look at the three specific stories that show how mechanics shapes the world. First, let's look at the sky. The Saturn V rocket. This is a machine that took humanity to the moon in 1969. Now, imagine you are the engineer designing this. What is your biggest problem? It's gravity, right? You need to lift this mass object off the ground. To do that, you need incredibly powerful engines. When those engines fire, they generate millions of pounds of thrust. Think about the mechanics here. The engines are at the bottom, pushing up. The heavy fuel tanks and the payload are on top, pushing down due to gravity. So what is the state of the rocket's body? It's being squeezed, it's under compression, right? The whole structure is under immense compressive load along its longitudinal axis, which is a vertical axis. But that's not all. As the rocket fell through the atmosphere, the wind hit it from the side. We call this aerodynamic force, and this tries to snap the rocket in half. That creates a bending moment, and then you have small thrusters firing to steer the rocket, which is actually the roll control. This apply a twisting force, which we call torsion. So you have this complex loading situation: compression, bending, torsion. How do you choose a material? Can we use stainless steel? Steel is very strong, right? Why not steel? Exactly, it's too heavy. If you build this out of solid steel, it will never leave the launch pad because the density is too high. So engineers had to use aluminum alloys and titanium alloys. These materials offer high strength but are much lighter. They also use something called a honeycomb sandwich structure. Image two thin sheets of metal with a honeycomb shape in between. This makes the wall very stiff but mostly empty space, which means it's very lightweight. This is a classical example of design for stiffness relative to weight. The second example is basiscape terraced. Now let's go from the stars to the bottom of the ocean. The basiscape trieste. In 1960, it went to the deepest point on the Earth, the Mariana Trench. Does anyone know what the water pressure is down there? It is 110 megapascal. 110 megapascals. To give you a sense of scale, the air pressure around us is 0.1 megapascal. So the pressure down there is around 1,100 times greater than what you are feeling right now. It's like having an elephant sitting on your thumb. Look at the design of the screw cabin. The little bore at the bottom. Why is designed in spherical shape? Why didn't build a nice, comfortable rectangular room? A box would be easier to stand up in, right? Yes, it's about pressure distribution. A sphere is perfectly symmetrical. When the water pushes on it from all sides, the load is distributed evenly as uniform compression. There are no corners. If you have a square box, the corners are stress concentrators, which means its weak points. Under 110 megapascal, a box would get crushed instantly. But a sphere directs all that force into compressing the material, uh, which this kind of steel can handle it very well. Also, look at the cables holding the sphere. Those are in tension, and when the vessel is being deployed or moved by the waves, the connection point experiences bending and torsion, right? So again, even in a submarine, we see all our basic deformation modes. Right? We finished the rocket and uh, the trieste. Let's look at something more familiar. The Statue of Liberty. She looks like a solid statue, but mechanically she is a complex structure. She has two main parts. One is a central pollen, and another is a copper skin outside. Here is an engineering challenge. New York City has hot summers and freezing winters. When metal gets hot, what does it do? It expands. When it gets cold, it shrinks. The copper skin is very thin. The iron frame is very thick. They expand and contract at different rates. If you simply nail the copper skin directly to the iron frame tightly, what would happen? As the skin tries to expand in the summer, the frame would hold it back. The skin would wrinkle, right, or even tear. It would destroy itself. So how did the designer solve this? Look at the diagram on the slide. They used armature bars. These are flexible bars that act as springs or like springs. They hold the skin in tension to keep it upright against the wind, but they allow the skin to float or slide slightly relative to the pollen. This way, the skin can expand freely without fighting the frame. Also, consider the wind. The statue holds a torch uh, high up in the air. When the wind blows, that arm acts as like a beam. It creates a massive bending moment and torsion at the shoulder. The internal pollen has to be stiff enough to resist this, so the arm doesn't snap off. Now, those were success stories, but in engineering, we often learn more from our failures. If you mess up the strength calculation, things break. If you mess up the stiffness or stability condition, things collapse. Let's look at two famous disasters that changed how we do engineering. The first one, this is the Tacoma Narrow Bridge. It was built in Washington state and opened to traffic on July 1st, 1940. It was a beautiful bridge, the longest suspension bridge of that time. Engineers were very proud of it. They wanted to look sleek and slender. But almost immediately, 4 months later, people noticed something was wrong. Even in a light breeze, the bridge would move. Locals nicknamed it like the vibrating. Only 4 months later, on November 7, 1940, it collapsed. Let's watch the video. What is happening here? Is the bridge just bending down under weight? No. Look closely. It is twisting. One side goes up, the other side goes down. It is oscillating. Why? The designers made a critical mistake on the aerodynamics and stiffness. Look at the compression on the slide. Look at the comparison on the slide. The ordinary bridge usually use open trusses. Wind can blow through them, but the Tacoma Narrow Bridge used a solid plate. It looks like a solid wall. When the wind hits the solid wall, it couldn't pass through. It had to go around. This creates a very famous phenomenon called common vortex strait. This vortex pushes the bridge up and down periodically. Unfortunately, that kind of oscillation matches the natural frequency of the bridge. This is called resonance. Right? The bridge starts to twist more and more and ultimately collapse. It exceeds the fatigue limit and snapped. Sadly, there was a dog named Tubby was left in the car on the bridge and died during the collapse. This disaster taught us that stiffness is just as important as strength. The bridge was strong enough to hold cars, but wasn't stiff enough to resist the wind oscillation. Our final story is terrifying. Image you have sitting on an airplane flying at 24,000 feet. Suddenly, there's a loud bang, right? And you look up, and the roof is gone. You are looking at the open sky. This happened on Aloha Airlines Flight 243 in 1988. A huge section of the airplane skin just peeled off. Well, um, immediately the pilots managed to land the plane, right? But the fortunate thing is that all the passengers is alive. I can only say, okay, it's alive, although they may get injured, but at least they survived. Trajectory. One flight attendant was swept out of the plane and died. That's a sad story. How did this happen? It's different from the Tacoma Narrow Bridge due to the wind oscillation. It's actually something called fatigue. Think about a pepper chip. If you bend it once, it's fine. If you bend it back and forth 100 times, what happens? It breaks, right? Even though you aren't pulling hard, the repeated cycle weakens the material. An airplane is a pressure vessel. On the ground, the pressure inside is low. On the air, we pressurize the cabin so you can breathe. This kind of pressurization makes the pressure inside much higher than the outside, right? The pressurization and the release of the pressure is a cyclic loading. Expand, shrink, expand, shrink. Aloha Airlines used this plan for short island hops. It had a huge number of takeoff and landing cycles. Tiny microscopic cracks formed around the screws. Because poor maintenance, nobody noticed this kind of cracks. Finally, on April 28, 1988, those tiny cracks connected and the skin just unzipped. This is why mechanics of materials matters. We study fatigue so we can predict how long the material will last before it falls from cyclic loading. We study fracture mechanics so we know how big a crack can get before it becomes dangerous. Although these are more advanced course, but at least in this class you will learn some basic concepts and prepare for those kind of course. So when you are doing your homework this semester and you get frustrated with the calculations, remember, you aren't just solving math problems. You are learning how to keep bridges standing and airplanes safe. You are learning how to protect people. Okay, with these stories in mind, let's look at how we actually model these things mathematically. Let's talk about the difference between rigid bodies and deformable bodies. In your previous class, statics, you are mostly deal with rigid bodies. What does rigid mean? It means that no matter how much force you apply, the object never changes shape or its size. It's essentially infinitely strong. Of course, that's an idealization. In the real world, nothing is truly rigid. Here is an example. If I put a tiny ant on the large steel block, the weight of the ant is so small that the steel block efficiently acts as a rigid body. But if I put the same steel block into a hydraulic press and squeeze it, it will deform, it will shrink or bungle, or even crack and damage. So in statics, you only cared about the overall load carry, the equilibrium, and the motion dynamics. In this course, the mechanics of deformable bodies, we care about the deformation, the change in shape and size due to the load. We are moving from the idealized world to the real world. Now, analyzing real material is complicated because real material are messy. They have defects, cracks, and complex microstructures. To make the mass manageable for engineers, we make 3 key assumptions or idealizations for those kind of deformable bodies. The assumption 1, continuous. We assume that material has no voids, no cracks, and no empty space inside. It is a solid, a continuous block. Is this true? Well, if you look at this plastic box, it looks continuous to your eyes. But if you zoom into the atomic level, you see atoms and a lot of empty space between the atoms, which is vacuum. So strictly speaking, matter is not continuous, but for engineering design, as the skill of bridges, cars, and buildings, we can ignore those atoms. We assume this solid is continuous. The assumption 2, homogeneous. This means the material properties are uniform everywhere. Think about a car wheel. Is the wheel homogeneous? No, it has a rubber tire and a metal rim. Those are different materials, but if you cut out a small piece of the aluminum rim, that piece is homogeneous. So homogeneity depends on the length scale you are looking at. In this course, unless I say otherwise, we assume the material is the same throughout the part. Well, assumption 3, isotropic. This means the material behaves identically in all directions. Metals, glass, and plastics are usually isotropic. It doesn't matter if you pull them up and down or left to right. They resist the loads the same way. A great counterexample is wood or timber. Wood is anisotropic. Think about a tree trunk. It has fibers running vertically. If you pull it along the fibers, it's very strong. But if you push it from the side, which is perpendicular to the fibers, it's much weaker and softer. Because the properties depends on the direction. Wood is not isotropic. But for this class, we will mostly deal with isotropic materials like steel and aluminum. Then let's talk about units. This is a math-heavy course, and units are where a lot of mistakes happen. I highly recommend you stick to SI units, which is the international system. Length in meters, force in newtons, stress in pascals, or Newton per square meter, right? I know we live in the U.S. and you are used to the U.S. customary system, which typically use pounds, inches, feet, etc. But in the U.S. system, it's a nightmare for calculations. For example, converting mile into feet involves a number of I don't exactly remember the number, but it's a very complex number. Converting mass to force involves gravity as 32.2 feet per second square, right? It's a little bit messy. In SI units, everything is ton-based, right? It's much clearer. If we talk about the units, then we must talk about the prefixes. Be very careful with the prefixes. In engineering, numbers are either too huge or too tiny. We don't say 200 billion pascals. We usually say 200 gigapascals, right? We need to know this by heart. Giga means 10 to the power of 9. Mega means 10 to the power of 6. Kilo means 10 to the power of 3. Micro means 10 to the power of negative 6. Nano means 10 to the negative 9. Pay attention here if you are doing calculations involving a square root. You must convert that giga to 10 to the power of 9 before you take the square root. For example, the square root of 1 is 1, the square root of 10 is about 3.16. If you mess up the power of 10, your answer won't just be a little off, it would be wrong by an order of magnitude. So always double check your prefixes. Okay, then we go to a quick math review. I know you know this, but it's a refresh. Scalars have magnitude only, and vectors have both magnitude and direction. Since force is a vector, we have two ways to multiply them. The first way is the dot product. The dot product will give you a scalar. It's essentially a projection. It matters how much of the vector A is pointing in the direction of vector B. And the second multiplication method is the cross product. This gives you a new vector. We use this for calculating moments and torque. Okay, here's a crucial reminder. Direction follows the right-hand rule. Curl your finger from vector A to vector B, and your thumb points in the direction of the result. We use this a lot when we talk about torsion and bending moments. Finally, let's talk about the calculus. Derivatives represents a rate of change, which is a slope of a curve. In the first part of the course, we don't use calculus much, but when we get to beams, we have to. Why? Because when you bend a beam, the top surface may be in compression while the bottom is in tension. There is a transition of stress across the height. That variation, the change in space, is a derivative. This leads us to differential equations. Now, I know differential equations sound scary. You may be thinking of complex proofs from your math class. Relax. In this course, we mostly deal with simple second-order differential equations. They usually look like this. dy over dx equals fx. Right? How do you solve this? We just multiply by dx and integrate both sides. Then we get y equals the integration of fx over dx. So honestly, if you can do basic integration, you can solve the differential equations in this course. We aren't doing magic here, we're just adding up the small changes to get the total deformation. Okay, that brings us to the end of lecture 1. We have covered the logistics, the three key concepts: strength, stiffness, and stability, the importance of simulation, and the basic assumptions we will use.